Hi, welcome to the first rule of acquisition. This is the fourth edition of the rules of acquisition. This version of the first rule of acquisition supersedes all other previous versions. The first rule of acquisition is correct answers prove nothing except utility. This is the improvement over the previous version being just correct answers prove nothing, which really isn't true because it does prove that your model or theory is useful. Okay, there's a widely held fallacy that in science, if your theory agrees with your observation, your experimental data, that your theory must be the irrefutable truth of the universe. And I will show, and the important thing here is that's not true. And I'm not the first person to say this. Okay, Karl Popper pretty much said, logically, no number of positive outcomes at the level of experimental testing can confirm a theory to be true, but a single counterexample can show a theory to be false. And again, this was echoed by Einstein. No amount of experimentation can prove me right. I'm assuming he's talking about his theories. A single experiment can prove me wrong. Okay, but these things are not widely taught. You wouldn't be surprised how many people that when I show these to, they're like stunned and like can't believe it. And they try to go off into this self-denial. Oh, no, that doesn't mean that. That means something else, yada, yada, yada. It means exactly what it says. And I'm going to show you. The problem is they don't, these things, these little sayings here don't adequately explain why. And I'm going to show you why. I'm going to show you why with a simple experiment where it's possible to get identical answers from 4 different theories. One of those theories being complete fantasy. Okay, and the first rule of acquisition is called, the title is the correct answer fallacy, and the first rule is the correct answers prove nothing except utility. Utility being defined as usefulness. And usefulness leads to technological advancement. Technological advancement is then the requirement for expanding our footprint in the universe. Our footprint in the universe is how far we can travel in the universe, how deep we can go in the oceans, how sensitive we can make measurements, how precise we can make measurements, what our knowledge and understanding, our theories, are pretty much our capabilities in our knowledge. And so correct answers will only prove that your model or theory is useful. And then I'm going to show that trying to prove truth is a fool's errand. Okay, and the first rule of acquisition is the cornerstone, I don't want to say supreme, of other rules of acquisition. For example, rule of acquisition 11.2, irrefutability does not prove exclusivity. In other words, just because you have a theory that gives you right answers does not prove that there's not another theory out there that can't give you the same equally good answers. Because when I did my graduate thesis and the dean of the School of Engineering said, well, what are you doing? I said, well, I'm showing new models of electromagnetism. He goes, ridiculous, Maxwell's equations are irrefutable. Well, so what? That doesn't mean there's not another way. Because one of the differences between engineers and physicists, I don't understand what physicists are taught. They seem to be taught that there's only one right way. Engineers are taught over and over and over again there's more than one right way to solve a problem. Or maybe I should say it differently. There's more than one way to solve a problem. And what's the simple experiment? The simple experiment are 3 loops of wire of different gauge conductors and similar area. And then what we're going to do is compute the area, the inductance of these wire loops with the 4 different models, and then measure and compare. And these are basically the experiment from the foundation series. These 3 loops come from the quad loop experiment, but I'm only using 3 of the 4 loops. Okay, so we already know what the experimental data of these are. And the parameter of the loops, the radial diameter, or the radius of the loop is given by A, and B is the cross-sectional radius of the wire itself, in case this picture doesn't make sense to you. Okay, and all 3 loops have the same radius, meaning this radius, loop radius, but each has a different wire thickness, and that would be the wire radius B. And these are the 3 gauges that were used. These were the measurements made in the foundation series. The reason why there's 2 sets is we took 2 sets of measurements just to make sure, to see what the repeatability of the instrument was. And so it looks like we're within 5 or 10 nanohenries. This is nanohenries, and this is the gauge of wire going this way. So we're within 10 nanohenries of each other, which is a pretty good measurement. 10 nanohenries means it's pretty much a 1% measurement, which is pretty respectable. Now, the theories. There are 4 different theories that we're going to apply to this experiment. We're going to use 2 theories come from classical physics, which use the Biot-Savart model here, which shows that the magnetic field, the B field, is transverse to a moving charge. This little symbol here denotes a charge. This little arrow denotes what direction it's moving in. And these little lobes here denote that the energy goes out transverse to a moving charge. And this is denoted by a cross product here. So this is essentially, this isn't the containment, this is the line of uniform amplitude, is what that is. Okay, the next 2 are based on different models that were found through computer search in the rhombus experiment, which is EMF 002T. One of those models has its magnetic field, which is longitudinal to the motion of the charge, and the other one has its magnetic field is a spherical entity relative to a moving charge. Okay, so we're going to have 2 theories based on this, 1 theory based on this, and one other theory based on this. So the first theory, we use Jackson's Classical Electrodynamics 3rd edition. On page 234, they use a derivation which uses the same parameters we're using. We decided to use his same parameters, so it would come out the same. And this is the value of inductance he gets with the computation. So let's see what that compares to the experimental data. Look, it's off a little bit. How about that? Well, it turns out Jackson does something here that all of us are told in school. We're told, and we believe it because that's what we're told, is he does a vector magnetic potential calculation to get the effect of the area containing the changing flux. And then he adds what this thing called intrinsic inductance. And we're told that that is the total of your self-inductance as an addition, of these 2 values here. Well, my friends, this is the equation for intrinsic inductance. It's in every textbook since the beginning of time, pretty much. It's a completely bogus derivation. I do this derivation in the foundation series and show you it's bogus. And what do I mean by that? I mean, they did the mathematics right. They did all their algebra right. They did all their... But the problem is they didn't follow the rules of electromagnetic physics, which has certain limitations on what you can do. And this boils into another rule of acquisition, which pretty much says math is a superset of nature. Just because you can derive something mathematically does not prove it exists in real life, and you should go and measure it to find that if your new math construct actually fits observation, then that's good. And so it's amazing to me that this is passed on book after book after book after book, and no one has bothered to verify it. This is the level of incompetence we're dealing with. And so when we remove this bogus intrinsic inductance from the equation, and so this little number here goes from minus 7/4 to minus 2. So this value has gone down a little bit because we removed this. Okay. And so now this is the corrected answer. And if we plot this corrected answer, we get pretty good alignment with experimental data. Okay. And then if we go to James Clerk Maxwell, Treatise on Electricity and Magnetism, Volume 2, Article 704, page 343, what he does is he calculates the coupling between 2 separate loops. This isn't a single loop anymore. This is the coupling between 2 separate loops. This is not what we're doing. Therefore, it's complete fantasy. And the loops are separated by the distance b, and the radius of each of the 2 parallel loops is a. And so if we plug b in to be the radius of the wire, in other words, if we use the radius of the wire and plug that in for b, then we get this answer here, which is identical to the Jackson value, which is natural log 8 over b minus 2. inside, blah, blah, blah. I don't have to plot it for you. It's the same numbers. And this equation is complete fantasy. And it gives us correct answers. Answers we can take to the bank. And then the new theories found in the foundation series, which is the foundation of new electromagnetism. Well, this is actually the foundation of new electromagnetism. And this gives us F equals ma. And so we've got Newton's equations appearing in electromagnetic measurements. That's another story for another day. Go look at the foundation series if that interests you. Okay, but when we plug these two in and we put them into the equation to compute the value of a loop, the values from these also converge on mu a, natural log a8 over b minus 2. I didn't actually solve these completely. What I did is I used numerical integration and I kept decreasing the delta volumes, and the results converge on this value as well. So I'm pretty sure if I did solve it algebraically, I would come up with this answer because the numerical methods converge on this answer. And so here we have three different field geometries. This one applied to a single loop, this one applied to a double loop, and they all get identically same answers. Identically same answers. Now, there's going to be some crusty old physicists out there that would say, oh, well, that must mean they all must be the same field model. Oh, that's pretty trivial. Oh, you just based them all on the same field model. No, wrong, 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 wrong. The convergence is due to the constraint of the application, not the constraint of the fields. The fields are three completely different fields. Okay, the thing is, what we've done is we've constrained all of these models to a closed loop of wire, and that's why they converge. And if you don't understand what that means, let me show you what it means. Assume we had four different functions of x. You plot them out, they're all very, very, very different, right? Well, if you converge, if you constrain all of these models to x equals 2, you're going to get identical answers. And that's the problem, is when you constrain what you're looking at, we only constrain everything to circular loops. And that's why these four field models all give the same, or these three, the field models all give the same answer. Okay, so constraining your observations will lead to ambiguity. You're going to have more than one theory that'll fit the data you have with excellent precision. And because our human footprint in the universe is constrained, my God, people, we have never sent a human being outside of the pull of gravity of the Earth. And all of our entire existence, history, everything we know is in that tiny little scum layer of the Earth, except for a couple of space probes and a couple of eyeballs looking at the universe. And yet we have the gall to say we know universal constants when we haven't traveled anywhere else but the little scum layer of the Earth. And we claim that some of our theories of the universe are universal laws. Really? We live on such a constrained footprint that we should expect that because we have very limited knowledge, that there's going to be more than one theory that will fit any given set of data that we have. And anybody who thinks that any given theory is an irrefutable truth is a moron of epic proportions. And let me give you an example. This is probably what I'm doing now with this example is now we're going to go the other way. We're going to show the same thing the other way. Okay? Let's say we have these four observations. These could be our, 4 observations that we have. In other words, that's a rate at which we can sample data. And so the easiest thing we humans do is fit a theory. The line would be a theory that fits all the observations. And all the line does is mimic what we observe. Okay, but then we have to practice and realize that because we may have a constrained footprint, that there may be more than one model that fits this data. And we have to go search for the other models, like I did for the field model. I did a computer search to find everything that would fit the inductance data. And when we do our search, we're going to have a polytheistic answer. Polytheism meaning more than one theory. And this is great. Now that we know that there's more than one theory to fit the data, what we have to do now is increase our footprint by increasing our ability to sample more tightly so that we can disambiguate. In other words, take a sample here, and then if the dot comes here or the dot comes here, we would know which is the more truthful answer and which is the less truthful answer. Okay? Rule of acquisition 1.1, because of our constrained footprint, we should expect and embrace polytheism. That means when we have some empirical data, we should go find every possible way to explain that data, every theory, every mathematical model. Because once we can find more than one that gives excellent results, well, then what we do is we go take more high detailed measurements to disambiguate which one it is. And therefore, instead of falling in love with the first one we got, imprinting like a little chicken, we're going to drive to the truth faster and faster. We're never going to get to the truth, but we're going to approach the truth faster and faster. Okay? And so, now we increased our footprint, our ability to measure. Now we can measure at a higher sample rate. And now we've disambiguated. But don't assume you're done, because nature can play a trick on you. And nature can still have another theory that fits even that expanded footprint. Okay, the truth may still be outside of our existing footprint. So don't get lulled into the fact that because everything that you know, and the blue dots are all we know right now, are fit by one theory, that's the only explanation. It's good enough for us to use to expand our footprint. And so, we conclude from this little diagram that it is impossible to prove a theory true. Because in order to prove a theory true, Rule of Acquisition 1.2, to prove a theory true requires infinite observations. And therefore, that's how you kind of read the semicolon, assume all theories are wrong. Okay, because again, the only way to disambiguate between this and this is to take another set of sample between here, but then you might find out there's another, it just keeps on going. So we will live with polytheism. I don't know why we got into this monotheism. So I think it's because we've been practicing monotheism for centuries that we automatically assumed in science there can only be one theory. I don't know why we humans are so retarded. And this leads to the footprint discovery paradigm. This is already in the Distinti New Science paradigms, and I'm going to repeat it here for those who haven't been through the New Science paradigm. Okay, so what we have to do is use whatever theories we have that adequately mimic what we presently know. And with those, we develop our technology, our utility, which will help us go faster, sample more precisely, reach farther out into the universe, do whatever we need to do with those models to expand our footprint. And then once we expand our footprint, that's usually when we find the observations that can prove our previous theories wrong and disambiguate the existing models. In other words, we're expanding our footprint to find the counterexamples. Because if we do things right within our existing footprint, the given theories we have should be irrefutable within our given footprint. Okay? In other words, if we properly design them, we're going to design them to fit everything we know properly. And it's when we expand our footprint, that's when we're most likely to find the counterexamples. And that's the footprint discovery paradigm. And it's actually kind of encoded in the first rule of acquisition, 1.3. Useful theories provide the technological advancement, the utility that expands a footprint to expose the counterexamples. And rule of acquisition 1.4, wrong theories can provide the utility to expand the footprint. They have to, because it's all we have. And we have to assume that they're wrong. We just don't know it yet. And that's exactly what Emile Lakatos. This used to be a rule of acquisition on its own in the earlier versions of the rules of acquisition. Emile Lakatos, we should not think that a theory is ultimately true, only that no counterexample has yet been found. And again, my thing is you have to expand your footprint usually to find the counterexamples. Dr. David Disney, the greatest obstacle to science is the illusion that we think we know what we're doing. Okay, beware of anybody who states that they have irrefutable knowledge about what anything is. If they say, well, I know exactly that this is that and that's a that, I can tell you right now they're a complete moron. The best we can do is mimic what nature does. Knowing what something does is not knowledge of what it is. And that's the third rule of acquisition, which is the utility fallacy, which reads monkey do does not mean monkey know. This, I think, going to make in its own rule of acquisition the scientific advancement paradigm. Haven't yet. It's still the fifth subset of the first rule of acquisition, or the fifth corollary or supporting statement of the first rule of acquisition. The scientific advancement is the replacement of wrong theories with more subtly wrong theories. Remember, we have to assume everything we know is wrong. The objective of science is to make them less and less wrong as our footprint expands. Okay, it's okay to use abstractions. What are abstractions? Abstractions are essentially lies. Okay, in other words, Ethereal Mechanics uses the dynamic binary ether model, which is very different than the classical ether model, which was static and unary. Okay, and relativity uses the fabric of space-time. They're okay to use these. It doesn't matter whether they exist or not, as long as they allow us to get correct answers to expand our footprint. But the important thing is the abstractions have to follow the rules of acquisition too. In other words, you can't, well, we have rule of acquisition 16 will cover the abstraction paradigm. An example of an abstraction is, like the contour lines on a topographical map. They don't really exist. You can't go out in your backyard and dig up the 200 feet above sea level line. But they're a good abstraction for representing a three-dimensional relief on a two-dimensional page. That's an abstraction, but it's very useful. But even that abstraction can't violate the rules of acquisition. And finally, to reiterate the monkey see, monkey do paradigm, all we have and will ever have are models that mimic our observations of nature. This is the monkey see, monkey do paradigm. These models were not handed to us by God on stone tablets. These models can and will be made obsolete as our footprint in the universe expands. Okay, this is the new structure for the rules of acquisition. You have the main number with no decimal point, and that's the title. The very, very first one, that is the main statement, 1.0. This would be the Ferengi title. This is the main one. This is the one that drives all of these. These are all supporting or corollaries to this. Sometimes they're restatements of this. Okay? And these are, we went over these. I'm not going to go over these with you. You can read them again on your own. Thank you. Thank you for being patient. I thank my Patreon members. If you want to help join, go to Patreon. Go to www.etherealmechanics.com. Thank you very much.